is just a little bit of a kind of explainer on Bose-Einstein condensation, just to kind of try and visualize it. So so keep an eye on both the motion and then also the energy states that you see as the temperature is decreased. So the increase in size is an increase in the de Broglie wavelength. So when they drop into when they all drop into the ground state, the point here is that that they're all described by as a single wave function. And so that single wave function, you know, when they're all in the same state, you have to describe all of even though they're individual particles, it makes the most sense to describe it as a single wave function. And when it's low energy, the wavelength is going to get large, and if it were zero energy, the wavelength would actually, you know, become infinite. But the uncertainty principle puts a limitation on how low it can actually, or how high it can actually go. But effectively infinite for the size of the atom. So now let me switch to sharing the slideshow. And I'm going to stop my video just because my wife is also on a meeting, so I want to don't want to overload our internet. Okay, so let me start this play. Okay, so this is the famous plot that was shared in 1995 for the first creation of a dilute gas Bose-Einstein condensate. So they used rubidium-87, and this was 1995. So this plot here is the velocity distribution. So you could think of the x and y axes as, I'm still talking with my hands as if you can see me, but the x and y axes on these plots as being like the x component of the velocity and the y component of the velocity, and then the height, which has the artificial color on it, as the number of atoms that would be in that state. So you could see when there's no Bose-Einstein condensate, it's kind of well distributed. And then when the Bose-Einstein condensate is first created, then you get that sharp peak at 0, 0, right? So at 0 velocity. And then they continue decreasing the temperature, and you get an almost pure Bose-Einstein condensate. So you get very few. So you know, in the middle picture, you get a fair amount of yellow and green in that picture, but things all kind of coalesce into that single peak. Now you would expect it to be exactly 0 width, right? Everything being exactly at 0 velocity, but you can't actually get that because of the Heisenberg uncertainty principle. And the fact that it's asymmetrical, right? I mean, if you kind of visualize it, the peak is not symmetrical, right? It's not round. It's sort of an elliptical cross section, and that's just the shape of their magnetic trap. So they have some sort of magnetic trap to keep all of the atoms together in a small confined space. So apparently it's got a different width in one direction versus the other. So this was the first creation of a pure Bose-Einstein condensate. You know, if you Google Bose-Einstein condensate, some of the suggested searches are, what is the fifth state of matter? So I remember that being, you know, kind of a headline in the 90s, and then in 2001 when they eventually won the Nobel Prize for this. Actually, the technique, the experimental technique of the cooling and trapping won a Nobel Prize before this did, which was in '97. Stephen Chu, who was the energy secretary under Obama, that was when he won his Nobel Prize in '97 for this technique that's applicable to other sorts of study of very cold systems. So then it was also realized that in superfluidity, as I was kind of talking about with, in response to Jarrett's question on Monday, superfluid helium-4, the superfluid state and the fact that it can flow without viscosity and it climbs up the walls of its containers and stuff, that's because some of the atoms within that liquid become a Bose-Einstein condensate, but it's a little bit different because that's within a liquid. So in a liquid, there are interactions between the particles, whereas in the gas, you know, even at this very low temperature, the gas particles basically don't interact with each other. It's all a statistical interaction. There's no force, but in a liquid, there is some sort of interatomic force. So that's, you know, that's the most famous application of Bose statistics. So let's move on to Fermi, Fermi Dirac statistics. So the first thing that we should do here, the important thing about Fermi statistics is that, and Fermi gases, is that there's a Fermi energy, right? So how do we calculate that? Right. So as we've done before, right, the primary calculation that we do is we normalize, right? So we want to integrate overall possible energies, right? Again, this familiar integral, volume times density of states times in this case, the Fermi Dirac distribution, integrated over all possible energies, should give us will give us the number of particles. So, you know, we have these integrals, but this one's actually easier if we look at zero temperature, where the Fermi energy has its clearest meaning, right? At zero temperature, that means that all the states below the Fermi energy are filled, and all the states above the Fermi energy are empty. Right, so that the Fermi energy still has the same value at other temperatures, but this is where we can really understand the meaning. So putting that into math terms, that means that a Fermi Dirac distribution becomes really simple. It's just a step function. So below the Fermi energy, it's just equal to 1, and above that, it's equal to 0. So that makes our integral easier. We don't have to integrate all the way to infinity. We just integrate to the Fermi energy. And I see that I left a factor out of this first integral here. It should be the same one as above. So I left out the F Fermi Dirac and the dE. But in the part where I spelled everything out, stuff in brackets, right? That just comes from the density of states, and then the density of states has a square root of energy in it, right? So we just need to integrate that from 0 to E Fermi. So that's an integral that, you know, we don't have to look up, and it doesn't give us weird square roots of pi's or things like that. Just integral of, you know, it's just a power, e to the 1/2. So we integrate that from 0 to E Fermi, and that gives us all that stuff in brackets times 2/3 E Fermi to the 3/2. Right, but what we really want to do is solve that. You know, we've done that integral, but now we want to solve this algebraic equation for the Fermi energy. Right, so, oops, didn't animate this one, but so we just copy that equation over again with the stuff spelled out, and solve that for E Fermi. So that gives us that it has, you know, these constants, and it depends on, really all it depends on is the mass of the particle, right? So the more mass of the particle, the lower the Fermi energy, and then it depends on the density, right? So it's the number density, right? So number of whatever they are, electrons, neutrons, atoms, whatever, to the 2/3, right? So per unit volume. So we can also, so we can use that Fermi energy now, and we could say, well, let's calculate the average energy, which is just the expectation value of the energy divided by a total number. I wrote it down as from 0 to infinity, but at 0 temperature, we would just integrate from 0 to E Fermi. And, that's again, a fairly straightforward integral, other than, making sure, you got to collect all your terms and, constants and stuff. But then you would get that the expectation value of the energy is 3/5 of the Fermi energy, right? So you have energies from 0 up to Fermi energy, but the expectation value of the energy is 3/5 of the Fermi energy. And that's at 0 temperature. So if you increase the temperature, of course, you're going to increase the energy of the average energy. Any questions at this point? All right. Okay, so now that we have that Fermi energy, okay, we can, this was the calculation that you've already done going back to nuclear physics, right? Where we were calculating the separation energy of the neutrons and protons, right? You had to include that part of there's the Fermi energy, and then there's also the, we were calculating the depth of the potential well, but yeah, the separation energy and then the Fermi energy. So we've already made some use of it just as a given, but now we were able to calculate it or derive it. So another example where we can use this is if we look at the conduction electrons in a metal, right? We can treat them as a free gas of electrons. Again, I didn't animate this one apparently. Actually, it's too overwhelming even for me. I'm gonna pretend you didn't see all of that. Okay. Example, sodium. So pure sodium is a metal. So what we do is we just say, okay, based on, you could do this calculation based on, some stuff from chemistry, right? You would say, well, what is the atomic, or what is the mass density of sodium? And then use the molar mass of sodium to convert that to a number density, right? Number of sodium atoms per unit volume. And then what are we really looking at? We're looking at the electrons, and so it's going to be the valence electrons. So for sodium, there's 1 valence electron per atom, so you wouldn't need to multiply that by any other factor. It's just the number of atoms per unit volume. So I swear I fixed that. Okay, the number density is 25.4 times 10 to the 28th per cubic meters, cubic meter. Yeah, and it's 25.4 per cubic nanometer. So move that decimal point over 1. I corrected it in the calculation. So then to calculate the Fermi energy, okay, so you might notice, well, or might not, I added some factors of C in the calculation for the Fermi energy. And that's because, you don't have to, but that's because I know what HC is, right? 1240 eV nanometers. And I know the mass of the electron in kilo electron volts is 511 kilo electron volts per C squared. So when you multiply that out, it makes the units take care of themselves a little bit better, rather than using anything else, right? So that's kind of a strategy, put in the C's when necessary, which we had been doing before as well. So so using those values, we can calculate, and we get that the Fermi energy is 3.15 electron volts. But I think that's a little bit, I mean, 3.15 electron volts, okay, that seems just order of magnitude, right? Electron volts make sense for electrons within an atom or within a metal, right? When we're doing photoelectric effect or things like that, right? Electron volts is something we would expect. But when we're talking about thermodynamics, I think it's helpful to compare that or to translate that to a temperature, right? So just divide that by Boltzmann's constant in the appropriate units, and you'll get a temperature, which we can call the Fermi temperature. And that's 36,540 Kelvin. So what does that mean? Well, that doesn't mean that the electrons within a metal are that hot, right? I mean, that would be crazy. That's not how hot a metal is. What it does give is a scale that we can compare things to. So when we say, well, at room temperature, 300 Kelvin, right? That's about 0.025, right? I think it's like 1/40th of an electron volt. So if we look at our Fermi distribution here, right, the number of electrons that are at a given energy within that sodium block. At 0 temperature, you'd follow that square root of energy all the way up to, here they just set it at 3. It must be a different metal. But then it would just drop off. But when you increase the temperature, you have to give some of the electrons just a little bit of energy, right? You're giving them 0.025 electron volts. So if you think about an electron that at 0 temperature is in the 1 electron volt energy level, that one can't gain any energy because it's a fermion, right? So to gain that amount of energy, it would still be, it would be at 1.025 electron volts, but that is already full, right? And you can't put extra electrons in a state that's already filled because they're fermions. So only the electrons that are at the highest, they're just below the Fermi energy. Some of them can be moved just above the Fermi energy. So the black line of the drop off then becomes that blue line of, okay, it drops off a little before the Fermi energy and extends a little beyond it, but not by much. Right? You'd have to start getting up to tens of thousands of degrees before we have to stop treating the electrons within a metal as where we have to really consider the effects of temperature. Right, so somebody is saying something in the chat.
Yeah, that was me.
Okay.
How did he get that temperature? 36,000.
No, it's not black body radiation. So I just took 3.15. I just took this Fermi energy and divided by the Boltzmann constant.
Oh, okay. EKT.
Yeah. Yeah. So E is equal to KT. So it gives us, it lets you put it in that scale. Now, the Boltzmann constant, we usually, well, I don't know the value, but you usually see it in joules per Kelvin, but you could just as easily write it in electron volts per Kelvin. Right. So that's all you have to do to calculate a Fermi temperature. That gives us, again, that doesn't mean that that's how hot the electrons are. That means that these, as long as your temperature is well below the Fermi temperature, then 0 temperature is a good approximation for any sort of thermodynamics calculation you'd want to do. So this is why, again, and we're going to talk about stars next, but this is why I can get away with saying that neutron stars are low temperature, even though they're, I don't know, 1,000,000 degrees, 100,000 degrees Kelvin. Other questions? Okay. So we won't do much more with looking at electrons in solids right now. That's something that we can talk about. we'll talk a little bit about when we do the solid state stuff. But I just want to say, there you can calculate with this lots of properties of materials. So things like heat capacity, right? How when you add heat to a metal, right, you are moving some of these electrons above the Fermi energy, right? And so how much energy or how much change in temperature do you get for a certain amount of heat, right? That's what a heat capacity is. So that can be calculated using this. You can also calculate the pressure. So really, you can understand, if you squeeze a metal, what pressure comes from the electrons just not being able to squeeze any closer together because all the available states are full. You can calculate that using this Fermi statistics. So maybe a more interesting application of not being able to squeeze things further together is what I'm calling degenerate stars. So I don't know who would be a good Charlie Sheen is a degenerate star. Maybe a little outdated reference. I'm sure he's still insane. He's just not, giving interviews right now. Anyway, so degenerate. Okay, we use this in physics to mean, when we talk about degeneracy, it's the number of states that have the same energy. Right. So here, when we're talking about something that's degenerate, that means that all of the available states are taken up. Right. So if you think about a star that is still burning, still doing fusion, it's really hot, and it's going to be a lot hotter than the Fermi temperature that you would calculate if you just said, let's take how many electrons are in the sun and how dense is the sun and calculate it. The sun is definitely hot, right? It's compared to its Fermi temperature. So what that means is that there are, if we look at the electrons in there, they're in excited states, right? And they might even be ionized, right? They're fully excited. But then once, and the sun, there's an inward force of gravity, but there's an outward force from that burning, right? So that's what keeps the sun at the volume that it is. But once that fusion stops, or mostly stops, it's going to start collapsing in on itself. So a white dwarf is what happens when, so you start collapsing things together, right? So then as you compress the atoms together, basically the electrons have to go into lower and lower states. And so they basically run out of room until they're in the lowest energy state within whatever atom they're in. Right. So if you tried to squish it anymore by gravity, the electrons, there is not a Coulomb repulsion, because everything's overall neutral. It's, hey, if you squeeze us any further, it's going to put two electrons in the same quantum state, and that's not allowed. So that's when you're fully degenerate, and we call that effective outward force a degeneracy pressure. Right, and then we'll see eventually if that pressure is large enough to overcome that, well, the electrons can't get any tighter packed, so all they can do is be absorbed by the protons in an electron capture. And then you get down to everything's basically neutrons, and you're going to get a neutron degeneracy pressure, right? Because neutrons are also fermions, so there's a limit to how far you can pack them. Okay, so let's look at the white dwarf. So the collapse is countered by the electron degeneracy pressure. So first we need to look at the gravitational energy. So if you've, well, I don't know, maybe in a mechanics class, or actually this is the same sort of calculation that we had for the Coulomb energy of the nucleus, right? Except instead of G and M on top, it was the 1/4 pi epsilon naught, and it was the charge, right? But it's basically the interaction energy of something from a 1/r² force. You get this 3/5. So it's depends on the mass of, all the mass, little bits of mass attracting the other bits of mass. When you do that integral, you get 3/5 m² and 1/r. So that's the radius. That r there is the radius of the sphere. Now this is using an assumption for a uniform density, which for a nucleus is a good assumption, but for a gravitationally attracted object, it's not actually a good assumption, right? The Earth is denser in the core than it is in the crust, and that's true for stars as well. But order of magnitude, that'll work. Okay, so let's just assume that the star, is all helium, right? White dwarfs are usually ones that are fairly low mass, so they tend to not have enough. They never get to the point of burning their helium into carbon and oxygen and those higher metals. That happens in the more massive stars. So these are things, as we'll see, they have to be below about 1.4 times the mass of the sun, right? So our sun will become a white dwarf in 10 billion years, I think, 5 billion years. So start planning. Humanity needs to start planning our retirement escape from the sun. Well, actually, we need to escape during the red giant phase because the sun will expand out to our orbit. So first things first. Maybe survive the coronavirus first. Okay. So if we assume that it's all helium, the mass then is going to be, okay, so I'm writing m alpha, but it would really be the mass of a helium molecule. It's just easier to type m alpha. Mailman's here. Luna's letting us know. So if we, can you hear my dog barking in the background? Yeah.
Yep.
Yeah. The mailman is one of her worst enemies because he comes in through the gate, but Kiki across the street is her other main worst enemy, but Kiki does not care about Luna. Okay, so if we assume it's all helium, you would take the number of heliums and times the mass of helium. But the reason why we have n/2 here is because that n is the number of electrons, right? Because we're looking at electron degeneracy pressure. And so we need to divide that by 2 because there's 2 electrons per helium. Right, so take that, plug it in to that classical physics calculation, and we get an expression for the gravitational energy. And that's negative because it's an attractive force. Okay, so now we also need to calculate the energy from the electron degeneracy pressure. So that's going to be, here's the total energy, right? So it's 3/5 times the Fermi energy, right? That's the average energy, and then multiply it by the total number of electrons. All right, so we would do that calculation based on, the definition of the Fermi energy, which we determined. Use the volume, we want to write that as a function of radius. So rather than just a generic volume, we would put in the 4/3 pi r cubed, which is the volume of the sphere. Put that in with electron mass and everything else, and we get that expression for the electron energy. Right. So the electron energy depends as 1/r², and the gravitational energy goes as 1/r. So that's important. The fact that they have different dependencies on the radius tells us that there is going to be some radius that minimizes the energy, right? The total energy. So the electron energy is positive, it's an outward pressure, and the gravitational energy is negative. So when we say, why would we say that we want to minimize the energy? Well, you're probably used to that now that, systems tend to minimize their energy. But really the way to think of that is that, remember that force is the derivative of energy. Right, so if I take the derivative of the energies, that's going to find the point where the force of gravity if I take the derivative and set it equal to 0, that's going to find the point where the force of gravity is equal to the force of the electron pressure. Right, so that's another way of thinking about why do we want to find the radius that minimizes the energy. Okay, so take those two terms, put them next to each other, and take the derivative, right? So you're going to have a derivative of 1 over r and a derivative of 1 over r squared, and lots of constants, but it's not actually, it's not messy or anything like that. Then you can just rearrange and solve for r. So it's a straightforward calculation, so I'm not showing the steps. So we get this, you would get this dependence for r. Trying to look at it and see, well, an important thing that we'll note is that it depends on 1 over the mass squared of the alpha particle. Although that's going to be the same, right? So really, when we start to look at neutron stars, it's going to be the fact that the neutron is more massive than the electron that's going to make the radius of a neutron star calculation, and that's going to be a much smaller value. So as an example, Sirius B, it's a white dwarf of just barely bigger than the sun, 1.05 solar masses, and the radius you get for that is 7.2 million meters. So what, 7.2 about 7,000 kilometers radius, right? So it's big, but it's not as big as the sun for sure. So now that's the calculation, 7.2 times 10 to the 6 meters. The actual measured radius is a little bit off from that. So what's that error? 1.6 out of 5.6. I don't know, 25 to 30% error. So I would say that's good.
How can
they measure the actual radius?
Yeah, how can they measure the actual radius?
As I was saying this, I knew somebody was going to ask, but I didn't think about it as I was writing the slides. How do you measure the radius of a distant star?
Couldn't you look through a telescope, and then based on how far away it is from where you are, you can use geometry to figure it out?
Use triangles.
Yeah,
I was thinking.
Yeah, there's a little bit of that. There's probably, well, so we can figure out how far away it is probably using parallax, meaning compare it to how, when we're in one edge of our orbit, it looks at like it's at a certain location, and then we're at the other edge of our orbit, it looks somewhere else, like it's somewhere else. So you can determine the distance that way. It's not, Sirius is not that far away, I think. I mean, it's definitely within our galaxy. Yeah. I don't know. I have never taken an astronomy class, so I'm not quite sure.
Why is it so why is it off by?
Well, I'm glad you asked. Right. So okay. So yeah, like I said, I think it's pretty good. Let's assume that the astronomers know how to measure these things, and that this is a good number. So okay, we just did this in this calculation in what, 10 minutes, right? Using some fairly basic statistical mechanics, and assuming that the star is at 0 temperature. So okay, So what are our sources of error on this? Well, so one source of error is going to be that we assumed a constant mass distribution, which is not going to be accurate. So that gravitational energy. Now, all that's going to do is change the constant multiple, right? So it's going to be something other than 3/5. So that's probably not going to change things by a ton. I mean, it's not going to be an order of magnitude error, but we're not off by an order of magnitude. So if it should actually be, 1, or it should actually be, 1/5, right? That's going to be enough to explain, or could partially be enough to explain that. But a bigger source of error is that the Fermi energy which we could calculate here, the Fermi energy is about 200 kiloelectron volts, and the mass of an electron is 511 kiloelectron volts. So you're starting to get an energy that's comparable to the rest energy, right? A kinetic energy that's comparable to the rest energy. So the electrons are relativistic, but they're not ultra relativistic, right? So that means that, okay, so we shouldn't go back and redo this calculation using the density of states for ultra relativistic. That would be even worse. But there is some relativistic correction to the density of states that we can't calculate. And so that's going to be a big contribution. So those are the two main sources of error. There'd be a somewhat of an effect. Now we could calculate, I didn't do it, well, I don't have anything to compare it to anyway. You could calculate the temperature that's associated with that Fermi energy, and then look up the temperature of the white dwarf and see, hey, how big of an effect is the temperature going to have on it? I would guess it's not that big, just because this is a common calculation and it's pretty good. But that's probably going to be some amount of correction from the fact that it's not actually zero temperature. Yeah, and if you ask me how they know the temperature of a star, that one I can answer for you. You look at the black body spectrum, just like we did last class, and you can figure out the temperature of the star. So that's an easy question. Okay, so now that correction becomes important, and it actually tells us a lot. So here's the two limits. Now we could go back, and it actually wouldn't be that hard. You can figure out when we did that calculation for the Fermi temperature, or the Fermi energy. We used the density of states that had the square root of E, right? That's an easy integral. If you did it, if you said, well, what's the Fermi energy of an ultra relativistic Fermi gas, you just have to integrate the one. It's got different stuff, it's got different constants, but that's whatever, you replace that, and it goes as E squared, right? So you could do that calculation just as easily, and we could do that. It's the green line here, the actual relativistic one, that's tough to do. So you can see for the low, so on the x-axis we have the mass of the star, and in the vertical axis is the radius. So if we look at about 1 solar mass, that's a fairly significant gap between the calculations of the non-relativistic one, which is what we did, and the relativistic correction. So you can see that that would largely explain the difference. Now, an interesting thing, you can see the ultra relativistic limit, right? At a certain value for the mass of the star, you get a Fermi energy that gets really high, right? Much higher than the mass of the electron. And in that limit, what happens is, so that ultra relativistic limit is called the Chandrasekhar limit, named after an Indian physicist. And so that limit is actually a limit to the largest possible mass for a white dwarf. So if a star is above 1.4 solar masses, it will not, there will never be enough degeneracy pressure to keep it from collapsing, right? And why is that? Well, the reason is if you take that the Fermi energy in the ultra relativistic limit, it's what we call softer, meaning it's not going to be, so when it fully goes as e squared instead of square root of e, there's less resistance to being packed together, right? There's more available states, and so those more available states can't, you can keep crushing things closer and closer together, even farther, and then at a certain point it's just going to gravitationally collapse, right? There's never going to be a radius. So remember I said that the fact that the electron energy goes as 1 over r squared, but the gravity goes as 1 over r. That was important because there is a minimum to that. Again, waving my finger around as if you can see, but if that energy has is going to be minimal at some radius. But if you use the ultra relativistic Fermi gas, then the electron energy also goes as 1 over r, right? So the gravitational energy goes as 1 over r, the electron energy goes as 1 over r. So there is no minimum, right? The minimum is actually at 0. So it would tend to collapse all the way, or until other physics kicks in. So that other physics that kicks in is when you get electrons so close to the protons, the protons are going to capture the electrons, right? So when that happens, they become ultra relativistic. The degeneracy pressure loses to gravity. Everything collapses in, and you get basically all neutrons, right? Okay, so here I said replace. Pretty sure this should be the electron mass, right? Because the alpha mass was just used in calculating or relating the mass of the star to the number of electrons, right? So here now we're looking at the Fermi energy of the neutrons rather than the electrons. So you do that same calculation, but you've got a neutron mass which is like 1,800 times bigger than the electron mass. And so when you do that, you find, say for 1.5 solar masses, you get a radius of 11 kilometers for neutron stars, right? So we went from 5,200 kilometers to 11 kilometers when you collapse from, or that's between a white dwarf and a neutron star. Right, so it's really the same calculation, you just with a different mass. So here I just kind of wanted to show that there's a little bit more detail, right? We pretend that they're all a single thing, but for the white dwarf, there's going to be so you actually could get some of them aren't going to be made out of oxygen and carbon, at least in the core. It's going to be crystalline. So it's kind of a weird state of almost solid matter, and you get the degeneracy pressure from the electrons. With the neutrons, it's even more complicated because we're making this approximation as if everything's made out of neutrons, but there's neutrons. There's still going to be some protons and electrons left over, and the very core we still don't know what it might be made out of. And so, one possibility is that there's another level that you can get to, right? So rather than, so what happens if you overcome the neutron degeneracy pressure? Well, one thing that happens is that you get a black hole, right? So if you overcome the degeneracy pressure of the neutrons, everything just collapses down until it gets to the point where it becomes a black hole. There's a calculation for what radius do you need for a given mass, what radius does it need to be compressed within, before it just becomes a singularity and a black hole. So that's definitely happens sometimes. What we don't know is some of these things that we call neutron stars might actually have a quark composition, right? So maybe it's possible that with enough degeneracy pressure, basically the neutrons would give off a W boson and become or one of the, it really would be one of the down quarks would give off a W boson and become a strange quark. And then where it says free quarks, and we know that they can't really be free, but it's kind of like the quark gluon plasma. You know, they're not by themselves, but they're also not within, you know, a known boson type particle. So it might be, you know, strange quark, just kind of unknown type of matter. You might just have some of the neutrons become lambdas, you know, the lambda, which was an up-down strange combination. We don't really know, because we don't know, you know, we know how to calculate electron degeneracy and neutron degeneracy, but we don't really know what the degeneracy pressure of this possible quark material would be. All right, so any questions? That's all I had on these things.